of this beautiful conference. And this session is going to be proofs of all the different kinds. And Liron will be the first speaker, so without much ado, please.
Hey everyone, I'm Liron, and I'm going to be presenting the talk on PCPs and instance compression from a cryptographic lens. This was a joint work together with Rothblum from the Technion. So let's begin by talking about the cryptographic lens. And what it essentially is a way for cryptographers to do the impossible. Cryptographers often assume that the adversary they're working against is computationally bounded instead of the classical unbounded adversary. And this allows them to construct objects which are classically impossible. In this work, we're going to use this method to bypass impossibility results for succinct PCPs and instance compression. So let's begin with a quick overview of PCPs, which you already know, so I'll do it quickly. A probabilistically checkable proof is a proof system for language L and NP. It consists of a lazy verifier who wants to know whether X belongs in L. So they contact a prover. The prover writes a PCP proof, and the verifier, being all lazy and all, only reads a few indices from the proof and decides whether to accept or reject. The requirements for PCPs are, first of all, completeness, which states that if X is true, then when interacting with the honest prover, the verifier accepts. And second of all is soundness. When X is false, when the verifier interacts with a malicious prover, but even against an unbounded malicious prover, which is denoted by these scary lightning bolts, for whichever proof this unbounded prover writes, the verifier rejects with good probability. All known PCPs have proof length, which is polynomial both in the length of the witness W and the instance X. And this can be problematic in some cases. And the example you should be thinking of is SAT, where the length of the proof or the assignment is polylogarithmic in the length of the instance. Where the instance is very, very long and the witness is very short, the proof ends up being too long. And ideally, we'd like there to be succinct proofs or succinct PCPs, where the length of the proof is polynomial in the length of the witness and not the much longer instance. But unfortunately, Antonina showed back in 2011 that succinct PCPs for SAT cannot exist unless the polynomial hierarchy collapses. But perhaps we can have something that is very close. And here we use a cryptographic perspective and consider probabilistically checkable arguments, or PCAs, defined by Kolokolova back in 2009. A PCA is a computational analog of a PCP. So what this means is, instead of having regular soundness or unconditional soundness, we have computational soundness against computationally bounded adversaries. So if X is false, when interacting with a malicious prover that previously had scary lightning bolts to mean that it is unbounded, here we remove the lightning bolts to emphasize that the adversary is computationally bounded. And when reading the proof written by this computationally bounded adversary, the verifier rejects. So these are PCAs. And a natural question is whether there exists succinct PCAs for SAT. And Kolokolova actually showed back in 2009 that succinct PCAs for SAT do exist, assuming crypto, but there are two major caveats. The first caveat is that this construction is designated verifier, meaning the prover only writes the proof for one specific verifier. No one else can verify. And this is unlike with PCPs, where everyone can verify a PCP proof. So this is the first caveat. And the second caveat is that their PCA construction has super constant query complexity. It's actually not bad. It's polylogarithmic, but it's not quite as good as PCPs, which have constant query complexity. And in our work, we actually get rid of both of these caveats. So what we do is in theorem 1, we assume sub-exponential LWE and standard cryptographic assumption. And for every bounded depth and P relation, we show that there exist publicly verifiable, constant query, succinct PCAs. So what this means is your favorite NP relation has a succinct PCA, which is publicly verifiable, meaning that everyone can verify it. And this verification can be done using a constant number of queries, just like in PCPs, except that here the proof is much shorter. It is succinct, comparable to witness length. So an application of PCAs is in the field of hardness of approximation. This is usually attributed to PCPs, but it can be interesting to know whether the slider notion of a PCA can suffice when showing hardness of approximation. And actually in our paper, we show that it does suffice. We use PCAs to reprove known hardness of approximation results. So what we do is we show a proof sketch for the following fact. The search variant of MaxSat is hard to approximate. This was already known from PCPs, but we show that this is provable using the slider tool of PCAs. So now that we know that PCAs can show hardness of approximation, an open question that remains is whether they can show new hardness results. And we leave that open question for future work. So now we move on to the second point about instance compression, originally defined by Harnik and al. Back in 2010. Instance compression is the following notion. Say you have a long instance X with a short witness W, like before, sat with long formulas and short assignments. An instance compression is a polytime function f, which maps the instance X into a shorter instance X prime. The length of X prime is polynomial in the length of the witness W. So here we actually compress the instance, hence the name instance compression. Moreover, instance compression also requires that X prime is true if and only if X is true. This means that there exists a witness W prime for X prime if and only if there exists a witness W for X. This notion has many applications, but unfortunately, Fon N Antonina showed that instance compression for SAT is impossible, assuming the polynomial hierarchy doesn't collapse. So once again, we bypass this impossibility result using cryptography. In our work, we define computational instance compression, which is a very similar notion in the sense that it allows for compressing of long instances down to witness length, but that there are a few differences. The first difference is that we require that if X is true, then X prime is true, similar to before. Second of all, we require that if X is false, then it is intractable to find a witness W prime for X prime. Note that it says intractable and not impossible, because even for false X's, there might exist a witness W prime for X prime, but we require that it be intractable to find it within reasonable time. And lastly, we require that there also be a polytime function G, which allows you to map a witness W into a witness W prime, hence being able to prove that the original X was true if you had a witness for it. In theorem 2, we showed that assuming the same cryptographic assumption, namely sub-exponential LWE, then for every bounded depth NP relation, there exists a computational instance compression scheme to SAT. So once again, this means that your favorite NP relation is compressible down to SAT. To conclude, in our work, we assume standard cryptography, and for a large subclass of NP relations, we first of all show that there exist succinct PCAs, which can be used to show hardness of approximation results. Second of all, we show that there exists computational instance compression, and thus we overcome the impossibility results for succinct PCPs and instance compression. Thanks for listening.
Excellent. Any questions you could post in the chat? You can.
I have a question, if I may.
Sure.
In your theorem statements, you had for every bounded depth NP relation. What do you mean by bounded depth here?
So these are relations that can be verified by low depth circuits. So log space uniform NC. So okay. An NP relation is can be verified generally by a P circuit, but we only have a result for a circuit for relations that can be verified by log space uniform NC circuits.
So I guess this matters in your setting. I mean, in general, you can always make the verifier like 3CNF, but in your setting, you cannot, because you're decoupling, I guess, input length from witness length.
Yes.
Okay. Thanks.
Sure.
Okay, more questions, comments, or?
Actually, if I may, so what does it show? What does it show up? This limitation of the bounded depth? Is that
What's the?
What does this limitation of the bounded depth come up? What technique requires this assumption on the MP relation as opposed to like a polynomial size verifier?
It's derived from the SNARGs that we use, the proof systems that we use that originally GKR, the proof system GKR has this limitation.
And they only know, okay, I see. Thanks.
Maybe just add that it's entirely possible that we could get rid of this limitation using no reason why it should be inherent.
Yep.
Right.
Thank you so much. This is great. So maybe Liron, thank you so much for great talk. If you don't mind stopping sharing, and Guy, you're the next one. Yeah.
Yes, hi, can you hear me?
Yes, excellent. So Guy Goldberg is the next speaker, please.
Hi, yes, so I'm Guy. I'm a PhD student at the Weizmann Institute of Science. And I'm going to talk today about the joint work with Guy Rothblum about the sample-based proofs of proximity. And before I present the model we study in this work, let's begin with the following problem. Say that I have two strings and I want to check if they are identical or far from each other. That is that I need to change at least an epsilon fraction of the bits of one string to get to the second string. And also, let's assume that we need to reject such bad inputs only with high probability, say 2/3. So there is a very simple algorithm for this problem. Simply choose uniformly at random an index j from 1 to n, query y at index j, query z at index j, check if they are equal or not, and repeat this simple test for enough times. So what we get is, we call this algorithm a tester. We get a tester with query complexity. The number of bits it needs to read from the input is about 1/epsilon. And for this algorithm to work, we really need to have the ability to query the input at arbitrary locations of our choice. Another model that of input access that we can consider is a sample-based access. It appears, for example, in machine learning settings. So in this type of access, we get samples of the input. Each sample is of the form xi, so we get the location of the sample and the value of the input at this location. And the samples are distributed uniformly at random, and they are independent of each other. So now we can no longer do what we did before. We cannot query y and z at the same location. So the best algorithm we can do for this problem, well, it's basically just draw samples at random, wait until you're lucky and find y and z at the same location, and test if it equals or not. And for a constant epsilon, by birthday paradox argument, we need to have at least square root of m samples in order to hit such a collision with a high probability. So now, can we somehow help this tester and reduce the number of samples it needs to draw? One possibility is to give him the help of a prover. So in an interactive proof of proximity, we now call the tester a verifier, and we allow it to communicate with untrusted prover. The prover is unlimited in its computational complexity for now. And we also assume it can read all of the input X, so we don't charge it for reading the input. And we, as in the previous talk, we need completeness and soundness. Completeness means that if X is in the input, if X is in the language, then the prover can convince us to accept the input. And for soundness, we relax the demand. We want that if X is epsilon far from the language, we want that no prover will be able to convince us to accept, except for a small probability of error. And now the verifier can have query access or sample access to the input. And now we are also measuring the communication complexity of the protocol, which is the total number of bits exchanged between the parties. And we want it to also be sublinear. So to put our work in context, we have the area of property testing where we don't have a prover, which is a wide field and well studied, mostly when the tester has query access to the input, but also when it has sample access. A recent line of work studies the power of those IPPs, interactive proofs of proximity, when the verifier has query access. And now in this new work, we study what is the power and limitations of such proofs of proximity when the verifier is restricted to have sample access to the input. So for the quality testing from before, we have a simple single round protocol, and it works as follows. First, the verifier draws a single sample, say that it was in index I. Now it sends I modulo n to the prover, which is like the relative index of this sample. In the completeness case, when y equals v, the prover sends to the verifier a single bit, which equals to yj, which is the same as zj. And the verifier checks that the value it got from the prover equals to the value of the sample. In the soundest case, when y is epsilon far from z, then with probability of epsilon, yj is going to be different than zj. And what can the prover do now? The point is that it doesn't know where the sample of the verifier were, if it was in the y part or in the z part. So the best it can do is to send a random bit to the verifier, and then with probability half, the verifier is going to catch it. By repeating this small protocol for enough times, we get a protocol with good soundness, and the sample complexity is 1 over epsilon, the communication complexity is logarithmic, and compare this to the square root n lower bound we had for a sample-based tester that couldn't use a prover. And in the paper, we generalize this protocol, and we show that if a language has a query-based tester, then it also has a sample-based interactive proof of proximity with good parameters. But what if the language doesn't have a query-based tester? Our main result is a reduction, and we show that if a language has a query-based interactive proof of proximity with some assumptions from this proof system, then it also has a sample-based interactive proof of proximity. And the overheads in terms of query sample complexity and communication complexity is not so bad. And why this reduction is useful? Because we know of rich families of languages that all of which has a query-based interactive proof of proximity. So now we can apply this reduction on those known families to show that they also have sample-based interactive proofs of proximities. And this might be a bit surprising because, as we saw with the quality testing, sample-based testers are much more restricted compared to query-based testers. So for tester, we lose power when we go to sample access. And here, in some sense, those models can be as powerful with some disclaimers. Okay, so what we do now with this reduction, we get the following two results. The first one is that every language which is computable in a low-def circuit is a sublinear sample-based interactive proof of proximity. And the second result is that every language which is computable in polynomial time and bounded polynomial space also has a sample-based interactive proof of proximity with, again, sublinear sample and communication complexities. And I'll note that those protocols are private coins and that they're interactive. So the verifier needs to talk with the program. Another two results, which I will end with them, are lower bounds for equality testing. The first one is regarding non-interactive proof systems, where the prover sends a single message to the verifier, like a proof, and we show for this a lower bound. And the second lower bound is for public coins proof systems, where the verifier is restricted to send only random bits to the prover during the protocol. And you can see the full video to see a proof sketch for the main reduction we show in the paper. Okay, thank you.
Wonderful. Thank you so much. Any questions? You could either
I can see the chat
or unmute, up to you. So actually, I have a very naive question. I was wondering if your results imply something for learning, kind of sample-based learning versus membership query-based learning, because there is a similar kind of.
So actually, Guy Rothblum had an earlier work on exactly that. So usually when you talk about learning, you're interested in beating the VC dimension and not in the size of the support of your distribution.
Mm-hmm.
So here we don't show anything which is specifically for the VC dimension and how to study with less samples than you need to in the general case. So here it's generic construction for any language.
Mm-hmm. Nice. Thank you. Yeah, this is really cool. Okay, Noah, are you here? Please.
Yeah.
Thank you.
Screen. There. All right. Can you guys see this?
It's not full screen yet, but
Yeah.
okay, now it is.
Here you go. Actually, let's. There we go. All right. Yeah. Thanks for coming to my talk. This is joint work with Tony and Robert. And you're going to see some extremely deep proofs. Yeah. So recently, several works have exhibited kind of a new type of trade-off, mostly in proof complexity. This is known as a supercritical trade-off. It's where when you restrict one parameter, like one resource, another one is pushed beyond the worst case. Yes, this has been seen primarily in proof complexity. Actually, I think the only examples I know of are in proof complexity. So first, Beambeck and Pagliazzo showed a supercritical trade-off between size and space for resolution. Following up on this, Razbarov showed an extremely strong type of supercritical trade-off. He showed that for the tree-like resolution proof system, if you restrict the width, then the size of these proofs blows up to be doubly exponential, like 2 to the 2 to the n. And then following this, a bunch of other works showed various trade-offs, mostly between resources such as width and size for proof systems and space. Okay, so in this work, we give the first supercritical trade-off between two very natural parameters of proofs, the size and the depth. And we do this for several proof systems. So resolution, KDNF resolution, and cutting planes. Okay, so I'll define very roughly what a proof system is, or what you should think of one as, and also what depth is. So a proof system is a method for producing proofs that a given CNF formula is unsatisfiable. So you start with a CNF formula, and we're going to think of it as a set of clauses. And you derive new lines from old ones using a set of sound inference rules. So the standard example is the resolution rule. You take two clauses with complementary literals, and you derive their disjunction, canceling out that complementary literal. So you can take these two clauses and derive X3, for example. And the goal is to derive the trivially false formula. And because these rules are sound, if you can derive the trivially false formula, then this is a proof that the initial formula had no satisfying assignments. So we can go ahead and do this, resolve these two clauses, and derive the empty clause. Okay, and this is the resolution proof system. And the two parameters we're going to be interested in here is size, which is roughly the number of inferences in the proof. In this case, it's 7. You need the initial clauses plus the 3 inferences you made, and the depth, which is the longest root to leaf path in the proof. Okay, so size is pretty natural, but depth is somewhat less studied. However, there's a good analogy between circuit complexity. So just like how in circuit complexity, depth sort of models parallelism, it's the same in proof complexity. So proof depth captures a notion of parallelism. This is pretty natural because a lot of proof systems model practical algorithms. So the resolution proof system captures the complexity of modern algorithms for SAT, and cutting planes captures classical integer programming algorithms. And then lower bounds on size imply lower bounds on runtime, and lower bounds on depth roughly lower bound parallelizability. Sorry. Okay, and in all proof systems that we are going to consider, depth is at most n. 1 second, let me try to make this better. There we go. Hopefully that's better. Yeah. Okay, so in all the proof systems we consider, depth is at most n. However, these depth n proofs may have exponential size. So in this work, yeah, we prove a supercritical trade-off between size and depth. So roughly, for any of the proof systems resolution, KD&F resolution, or cutting planes, we show that there's a C&F formula on n variables such that it has polynomial size proofs. However, any sub-exponential size proof must have polynomial depth, where this polynomial is greater than n. So above worst case. And our trade-off is smooth, so we can ramp this up. We can show that there's also a formula which has weakly exponential size proofs. However, any sub-exponential size proof must have weakly exponential depth. And very formally, our trade-off is as follows. I'll state it for resolution. The trade-offs for cutting planes and KD&F resolution are basically the same. The parameters change a little bit, which makes it annoying to state like a general theorem. But yeah, so if we let epsilon be some constant and C be a real valued parameter that'll control our trade-off, then there's a C&F formula which has proofs of size n to the C roughly. However, any sub-exponential size proof has to have the following trade-off between depth and size. So the depth times log of the size has to be about n to the C. So instantiating C gives us the trade-offs that you saw in the previous 2 slides. Okay, and I'm going to sketch a very rough idea of the proof. It's this hardness condensation technique from Razborov. So basically what we're going to do is we're going to start with a C&F formula on capital N many variables, which has small size proofs, but requires large depth. So these should be capital N's rather than little n's. Yeah, so you should think of this as polynomial in capital N being the size and requiring capital N depth. And then we're going to find a way to compress the number of variables while maintaining that both A and B hold. So we compress the little n. And the upshot is that the new formula that we get, F prime, is still going to require capital N depth, but only has little n many variables. So we get a supercritical depth lower bound for small size proofs. So how is compression done? We use a lifting theorem. So if you're familiar with lifting theorems, you take a formula, you compose, you replace each variable by a gadget of new variables. So x1 to xn are vectors of new variables. But our lifting theorem has a bit of a twist. These vectors of variables are no longer disjoint sets, so they overlap. And this overlap allows us to reduce the total number of variables. Yeah, so if here's a little picture. If you think of the Z variables as the original variables, there's capital N many of them. The X variables as being the new variables. And then the gadget G is, going to be defined by replacing each Z variable with some X variables from the pool of X variables, and they're indicated by the arrows. So for example, Z1 is replaced by X1 and x3, the gadget applied to those variables. So that's very roughly how the proof goes. And finally, some open problems. Obvious ones, like can you get supercritical sized-up trade-offs for other proof systems, such as Reslin or stabbing planes? And can you get supercritical sized-up trade-offs from monotone circuits? And in the extended version of this talk, I give a few other open problems, but they need a bit of motivation. They're basically approaches to getting this monotone circuit trade-off. All right, thanks.
Thank you so much. Excellent. Any questions? So just a quick question. So in your proofs, is there some reason why, say, Reslin seems harder to do than the one that you did? Or do you think you could just push the techniques that you have? Or does it require something?
For the proof systems that we get lower bounds, we already know nice lifting theorems, and we basically take advantage of those.
Okay.
For Reslin, it's not so clear. I'm not an expert on the state of the art of Reslin, but I think, so Reslin F2, we definitely don't have lower bounds on, like size lower bounds. And in some other cases, I think over the reals, we do have lower bounds. I'm not so sure there.
Oh, nice. That's extremely deep. Thank you. Okay, thank you so much. If no more questions, Stefan, I think you're the next one.
Yeah.
Yeah, please.
Okay, is my presentation visible?
It's not full page, but it's visible. Okay, that's better.
Oh, okay. All right, so let's get started. So hi, everyone, I'm Stefan. I'm a PhD student at McGill. And in this talk, I'll be talking about semi-algebraic proofs and algorithms. This is a joint work with Mika Göös, Noah Fleming, and Robert Robere. So let's start off with some background on extension complexity. So here we have sort of the classical picture of this concept, where you have a lower dimensional polytope P, and it possibly has many different defining facets. And what we would like is a higher dimensional polytope, P prime, with many fewer defining facets, which projects down to the original polytope P. So this was originally thought up in 1988 by Yannikakis, and the reason why this is useful is that it can drastically speed up linear programming. So rather than optimize over P, you can optimize over P prime and project downwards. And this is also a useful technique for giving lower bounds on linear programming. You can show that there's no small higher dimensional polytope. So let's give some formal definitions here. And rather than just for a single polytope, we'll work for a pair of polytopes, P and Q. So P will be an inner polytope and Q will be an outer polytope. And we call an extended formulation K of this pair to be a polytope in higher dimensions that when projected downward, it contains the inner polytope P and is contained by the outer polytope Q. So we can define extension complexity as the smallest extended formulation, in essence, that contains P and is contained by Q. So we minimize over all the extended formulations and we count the number of facets. So this minimization on its own is kind of hard to work with, so we'd like a more combinatorial representation. And in Yannikakis' original paper defining this topic, he showed this beautiful factorization theorem, where if you have this easily definable matrix called the slack matrix, representing distances between vertices of P and facets of Q, the non-negative rank of this matrix is equivalent to the extension complexity of this pair. So our goal will be to use, to understand extension complexity as sort of a circuit model for computing Boolean functions. And Yannikakis sort of preliminarily did this in his paper, where he showed that you can convert circuit gates to inequalities. So let's see how this works. So if we have a Boolean function f, we can define a separating polytope P of f. So the definition here is P will contain the convex hull of the ones of f, and it will have empty intersection with the zeros of f. So you can imagine if we want to compute f, if we have a separating polytope, all we need to know is if the input is inside the separating polytope, great. And if not, then it must be a zero. So here's just a picture sort of illustrating this, where P is containing the convex hull and has empty intersection with these zeros. And there's also a monotone version of a separating polytope, but there's some technicalities there, so I won't give its full definition. All right, so let's actually formalize the computational model. And so we want to utilize extension complexity, which means we need a pair of an inner and outer polytope. The inner polytope will be the convex hull of the ones, and we'll need an outer polytope. So here we give one. We can use what we call the Karchmer-Wigderson inequalities. So we define an inequality for every zero of the function f. So y is a 0. And on the left-hand side, we have Hamming distance. So this sum over indices of xi by 1 minus yi plus 1 minus xi by yi. We say this is at least 1. And the idea here is that any one of your function has to have Hamming distance at least 1 with any 0. And here below, you have pictorially what's going on, where we have the convex hull of the ones, and these inequalities are fleshed right up against it. There's also a monotone version of this, which is basically the same. And in general, since all we want is a separating polytope between the ones and the zeros, instead of just having a 1, you can have an epsilon. So an epsilon greater than 0 and less than or equal to 1. And this allows a bit more space. So if we show side by side Q of 1 and Q of epsilon, Q of 1 is right up against the inner polytope, whereas Q of epsilon allows more breathing room. So you can imagine if you're looking for extension complexity of a separating polytope, it might be much smaller with Q of epsilon. So we can actually define complexity measures using these. So on the left-hand side, we have SEP1 and monotone SEP1. And on the right-hand side, we have separation complexity and monotone separation complexity, where we're minimizing overall positive epsilon of this non-negative rank. And so it looks esoteric. However, Pavel Hrubesch showed that these are actually quite natural. SEP1 lower bounds formula size and separation complexity lower bounds circuit size. Likewise, monotone separation complexity lower bounds monotone circuit size. And just as a reminder, by Yannakakis' factorization theorem, another way to rewrite this, separation complexity is just the minimization over these epsilons, the extension complexity of the pair, the convex hull of the ones, and QF epsilon. So what we would like to do is take this analysis and apply it to query complexity and proof complexity. So we'll hop right into semi-algebraic proofs now. And so we start with conical Hunter degree. And all this is a certificate that your Boolean function is non-negative. And we do this by factorizing it into a conic sum of conjunctions we call juntas. So a junta is just a product of variables where some of them are multiplied positively and the others are, in a sense, negated with a 1 minus. So you can really just think of these as conjunctions, polynomial versions of conjunctions. And we see below, as an example, if you have the conjunction x1 and not x2 and x3 and x4, this is converted into multiplying x1, x3, x4, as well as 1 minus x2, since x2 is the only negated variable. So conical junta is just a conical sum of juntas, so all the coefficients are going to be at least 0. And we can define conical junta degree as just the minimal degree D, where you can represent your Boolean function as a conical junta. So for extension complexity, we had this slack matrix encapsulating extension complexity, and this matrix is non-negative. And when you factorize the slack matrix into these, a sum of non-negative rank 1 matrices, this is, in essence, a proof of its non-negativity. And so we do the exact same thing here for a specific polynomial, and we're going to show that it is non-negative by factoring into juntas. So what is this certain polynomial? It's the violations polynomial. So if we have an unsatisfiable CNFC, then we can define the viol of C as just the sum of the negated clauses. And so on an explicit input, this counts the number of violated clauses. And of course, since we assume that C is unsatisfiable, this means that the number of violations is always at least 1. So to prove that C is unsatisfiable, if all you need to do is show that a viol minus 1 is at least 0, or just for any epsilon between 0 and 1, showing that viol minus epsilon is greater than 0. So if we take that same representation we saw with separation complexity, doing this minimization, of conical Hunter degree of Weil minus epsilon, perhaps this is interesting. And our first result in this work is that this actually equals something very natural. It is equivalent to Shirali-Adams degree. So what is Shirali-Adams? Well, it's another proof system. So we're trying to verify that a CNF is unsatisfiable. And this is the proof system that corresponds with using linear programming for approximation algorithms. So it's a very natural proof system to study. And so it's also a generalization of conical Hunter degree. So below we have an example of what a Shirali-Adams refutation is. On the right-hand side, we have -1, so negative. And on the left-hand side, we have something that is non-negative, giving a contradiction. And so likewise with conical Hunter degree, Shirali-Adams degree is just the minimum degree D we need to give a Shirali-Adams refutation of C. And if you'd like to see more in general for semi-algebraic proof systems, I recommend seeing Noah's book on the topic. Back to our results. So we first showed that this minimization is equivalent to Shirali-Adams degree. So it's natural to ask, well, clearly this simulates conical Hunter degree, but what about the reverse? And so we answer this negatively, where we show that there is a family of CNFs in resolution that it can be done easily, that conical Hunter degree requires large degree, in fact, linear. And so this is known as the iteration problem. And we are able to use Kothari, Meka, Raghavendra's lifting theorem that lifts conical Hunter degree to negative rank. And we're able to translate this result to circuits. So in fact, we're able to separate monotone circuit complexity from MSEP1. So here is just a full picture of all of our results. So on the left-hand side, we have proof land, where we separate resolution from conical Hunter degree. And on the right-hand side, we have the lifted version. And additionally, we show feasible interpolation, which I won't fully get into, but it's just showing that you can take a proof and convert it into a computation verifying unsatisfiability. And we show that monotone separation complexity feasibly interpolates Shirali-Adams degree. And so in some upcoming work, we've also noted that a lot of these arguments also work for sums of squares. All right, so thank you for listening. Be happy to hear any questions you guys have.
Thank you so much. This is really cool. Any questions, any comments? So one question. So the conical Hunter degree corresponds to Shirali-Adams, right? Do you have similar kind of characterization? You mentioned SOS. Maybe for other systems, kind of going back from the proof systems to your characterizations.
Well, so the only other one we've considered is sum of squares. It might be interesting to look at other proof systems as well, but yeah, that's not something that we've considered.
Oh, really nice. Thank you. Anybody else? Questions, comments? Okay, then if you don't mind, stop and sharing, and Ian, please, the floor is all yours.
All right, you can see me, hear me?
Perfect.
All righty, thanks for sticking around to the last talk of the session. My name's Ian. I'm going to talk a little bit about lifting theorems and combinatorial sunflowers. And just want to shout out my co-authors. On the West Coast, there's Raghu Meka, Jiapeng Zhang, and Shachar Lovett. And then on this side, we've got Tony Pitassi, who is currently at Columbia. So I'm going to be talking today about the interplay between two computation models, decision trees and communication complexity. And I'm going to quickly define them and show why I think decision trees are weak and communication complexity is strong. So decision trees you've probably seen before. You can think of them as a rooted binary tree, where at every internal node you have the value, a label of an input variable, and the two edges coming off of the node are going to be labeled 0 and 1. And the idea is just that you ask what the value of that input variable is, and you go down the corresponding edge until you reach a leaf, at which point you announce the value of the function. So this is a non-uniform model in the sense that once you've read all of the variables, you know exactly what the value of the function is. And so the depth of this tree is at most n, and we're going to call the depth of this tree the decision tree complexity. And it's weak because for some very basic functions, such as the OR function, you can't do any better than n, really. So it's not too hard to come up with simple functions that are maximally hard for decision trees. On the other hand, in communication complexity, we're going to have two sets of variables. We're going to have some x variables and some y variables. And the x variables are going to be given to one player named Alice, and the y variables to the other player named Bob. And they're going to be computationally unbounded. There's no restriction on what they can compute, but because they only have half of the input each, they have to communicate somehow to solve the function. And we're going to measure communication complexity by the number of rounds it takes and the number of bits they're going to have to send in the worst case to compute the function. And again, we can look at this as a tree where each internal node is going to be now an arbitrary function over one half of the variables, so the other, either x or y. And again, they're just going to output a bit and you're going to follow accordingly. So this keeps track of the transcripts thus far. And the depth here again is at most, say n, where n is the smaller side because one of the players can just send their whole input. But for simple functions, for many simple functions, this is of course much less than n. And in fact, it captures some much more difficult notions such as formula depth. So this is a very strong model of computation. And the reason we were talking about these two models that seem quite different is that lifting, which Noah alluded to in his talk earlier, is going to be a generic strategy for turning lower bounds in the decision tree world, which are easy to come by, into lower bounds in the communication world, which is something we care a lot about and is a much harder task. And it's going to be generic in the sense of for any function that's hard for decision trees, we're going to cook up a function that's hard for communication. And specifically, it'll be this function. So we're going to take the original one-party function f and replace each variable zi with an inner function, which we call the gadget, g, applied to some fresh set of variables, xi and yi, which are split in the natural way between Alice and Bob. And the idea is, if we just gave Alice and Bob half the z variables each, they could express some more complicated relations over all the variables that they've got. Whereas if we split the value of each variable up between them, the hope is that they have to do a lot of communication to even learn about what these zi variables are. And so if we keep track of which variables they're communicating a lot about, it's like they're doing a decision tree, essentially. And to formalize this intuition, here's going to be our inner function. So the inner function is called the index gadget. It's parameterized by some number m, and Alice is going to get log m bits, which you can think of as a number from 1 to m, and Bob will get m bits, which we think of as an array of length m. And then the index gadget is simply the value in Bob's array pointed to by Alice's element. And this is pretty general in the sense of you can think of Alice as getting an input to a function and Bob is holding the truth table to it. So this captures a pretty naturally captures the kinds of inner functions we'd want to compute. And it turns out with this index gadget, you can actually prove the lifting theorem that you want. So this is kind of the original lifting theorem, and it's been refined and improved upon many times, but originally it was due to Ross and Mackenzie in the late 90s. What they show is that as long as you pick m large enough, some large polynomial in n, you can get that the communication complexity of this composed function is the decision tree complexity of the original unlifted function times this log m overhead to compute the index gadget. So just to see where that's coming from, let's see the easy direction. If you've got a decision tree for f, Alice and Bob can start at the root, and anytime they need to query a variable, say zi, Alice is going to send her entire value xi, log m bits, and then Bob will just send back the answer to the index gadget. And then they go down the appropriate edge of the decision tree and they keep going. And what we show in our paper, not today, you'll probably have to watch the full talk for the details, is that the other direction also holds. So just to say what we're contributing in this work, we developed a different technique for proving one of the central lemmas in this lifting result using combinatorial sunflowers. And the advantage is that it actually works for a very broadly for many of the lifting theorems that have been proven since that original result of Raz and McKenzie. It replaces, they all use different framing, and then they've got a slightly different central lemma that are proved in different ways. And we unify these all under one central lemma that's proved one way. And it, not only is it proved one way, but it's proved very, very simply. It's just an application of a lemma from combinatorics plus maybe a quarter to a half a page of framing. So this really eliminates a lot of the technical challenge involved in previous lifting proofs. And it also comes with it a quantitative improvement, which is that we can improve on the value of M that works for the lifting theorem. So the larger we make M, the worse our lower bounds we get out of this lifting result. And so improving M down to, say, a constant is the holy grail of lifting theorems. That's not an overused term. And what we do is we improve from all the previous numbers, which ranged from, say, n squared all the way up to n to the 256. We reduce them all to n to the 1 plus epsilon for any epsilon you pick. And that comes with the possibility of future improvement, which is that if you improve this sunflower lemma, you get immediately smaller gadgets. We've removed the dependence on M from everywhere else in the proof. Okay, so I don't have a lot of time, but I just want to say a couple of things about how the proof works. The whole idea is that our gadget is supposed to be obfuscating the variables. So we want to say that the important coordinates are the ones where Alice and Bob are communicating a lot of information about them. And what we hope from the index gadget is that for any variables where they haven't sent a lot of information, they know basically nothing about the value of the actual ZI variable computed by the index gadget. The way we track how much they've actually talked about a coordinate is by min entropy. So if you have some set of possible, from Bob's perspective, there's some possible set of values that Alice could be holding, determined by the protocol thus far. And we look at the minimum entropy, if you restrict to any of the particular coordinates CI, of the possibilities left for Alice's input on those coordinates. And this has the nice property that it's log m if everything's uniform, and 0 if it's not, and it decreases by at most 1 every time they send a bit, which means that after it will take them something like log m rounds before the min entropy drops by a constant factor, at which point whichever coordinate caused the min entropy to drop below this threshold, we can query that in our decision tree, and that we can be reasonably sure that's an important coordinate. And then where sunflowers come in is the opposite side, which is that if you look at all the coordinates that haven't been queried in the decision tree, as long as the min entropy is high, all possibilities are still available for the index gadget. So I can't go through the connection today. I would suggest taking a look at the paper or at the full talk. I just want to note that this actually closes off a loop, which was established by earlier work, which showed that if you could improve lifting theorems, query to communication lifting, you can actually get better results in combinatorics for the sunflower lemma. And now, again, we've shown that better sunflowers improves your lifting. So I think it would be nice to flesh out this connection more and see how deep it runs. And of course, it would be good to keep improving on the size of the gadget that we need, all the way down to order 1 would be fantastic. These can all be achieved by various combinatorial results, and we talk about it a little bit in the paper. And of course, it'd be nice to get this to work for gadgets, the other gadgets that we care about, like inner product. So that's basically it. Thanks.
Well, thank you so much. This is really cool. So any questions, comments, better sunflowers?
I have a question, if I may.
Yep.
Is your sunflower technique tailored for the index gadget, or could it work for other gadgets like IP? So I don't have a sense like how much sunflowers have to do with indexing as opposed to other things.
For the time being, it is specialized for the index gadget, but we've been thinking about how it might be applicable to something like inner product. Again, index gadget's very general in the sense of you can look at the larger side as a truth table, and you're applying sunflowers. When you apply the sunflower lemma, we're applying some randomized one where we think about a random set over a universe, which is like a random input to Bob's side. Once you go to like the inner product gadget, now it's not uniform over all possible sets. They're like they're very controlled. And so you have to come up with lemmas that are more specific for different distributions. If you know anything about approximate sunflowers, I guess the idea is like approximate sunflower lemma under different distributions. It's not out of the realm of possibility, though.
And so just a quick follow-up. Is your lifting also work for like randomized?
BPP is another thing we've been thinking a lot about. There, the parameters that we get from our main lemma are just slightly off in terms of the loss that you incur. We have like a multiplicative loss, and BPP requires an additive loss. But again, that's something we've been working on quite a bit. So I'll get back to you if we can think of anything.
Okay, thanks.
More questions, comments, if to Ian or maybe to other speakers? Well, thank you very much, everybody. It was fantastic session. So many cool things, and I guess we are well on time. We even have a couple of minutes to still hang around here before the next session starts. So thank you so much for this. This is wonderful.